Have you ever really stopped to think about how our world gets put together? I mean, everything from the phone in your pocket to the planes flying overhead, they're all made of millions of parts from factories all over the globe that somehow come together and just work. How on earth is that possible? Well, let's pull back the curtain on the invisible system that makes it all happen. Just think about this for a second. You've got a precision shaft being machined in Germany. At the same time, a housing for it is being drilled thousands of miles away in Texas. These parts have never met, yet when they show up on an assembly line, they fit together flawlessly. This isn't magic, and it's definitely not luck. It's the result of a very deliberate, worldwide agreement. The secret is this universal engineering language called interchangeability. It's built on a set of rules from the International Organization for Standardization, or ISO. Basically, this system makes sure that no matter where a part is made, it's going to fit its counterpart just like it's supposed to. And to really get this language, we need to start with its most basic vocabulary: the 3 types of fit. All right, so let's break down these 3 fundamental types of fit. It really all boils down to the relationship between a shaft, you can think of that as the male part, and a hole, which is the female part. First up, we've got the most common one, the clearance fit. It's simple. The shaft is always, guaranteed, smaller than the hole. This creates a gap, or clearance, and that's what lets the parts move freely. This is exactly what you'd want for something like a motor shaft spinning smoothly inside a bearing. The whole point here is movement. Next up is the transition fit, which is kind of like a balancing act. The size ranges for the shaft and the hole actually overlap just a tiny bit. So depending on the final sizes after manufacturing, you might get a really small gap or a little bit of pressure. So why would you do this? It's all about perfect alignment. Think about dowel pins that you use to locate 2 pieces of a machine jig. You don't want them loose, but you also don't need them locked in forever. Their one job is precision positioning. And finally, we have the interference fit, which you might also hear called a press fit. Now this is where it gets interesting. The shaft is intentionally made larger than the hole. Yeah, you heard that right. You can't just slide these pieces together. Nope. You need a big hydraulic press, or maybe you have to heat up the hole to make it expand while you freeze the shaft to make it shrink. When those parts get back to the same temperature, the force between them creates this incredibly powerful bond, basically turning them into one solid part. This is for when things must never, ever move. You know, this simple rule pretty much says it all. Clearance fits are for moving, transition fits are for positioning, and interference fits are for staying put. It's the core idea that guides every engineer's choice for just about any application. So now that we know the what, let's get into the how. How do engineers actually specify these fits so that any machine shop on the planet can understand what to do? This leads us to a little code you'll see on almost every single technical drawing out there. If you ever glance at an engineering blueprint, you're going to see these codes all over the place. H7/G6, H7/H6, H7/P6. I know it looks like some kind of secret code, but it's actually an incredibly clever shortcut. And have you noticed the pattern? That H7 for the hole, it's almost always the same. Turns out there's a really practical and very money-saving reason for that. It's called the hole basis system, and honestly, it's based on a super simple manufacturing reality. See, making a precise, standard-sized hole is pretty straightforward with tools like drills and reamers, but making a custom-sized hole, that gets difficult and expensive fast. On the flip side, turning a shaft down to a very, very specific diameter is actually pretty easy on a lathe, so engineers came up with this brilliant hack. They basically said, let's just agree on a standard, predictable hole size, that's our H7, and we'll just change the size of the shaft to get whatever fit we need. If you want a clearance fit, just make the shaft a little smaller. If you want an interference fit, make it a little bigger. This one principle simplifies manufacturing like you wouldn't believe and just slashes costs. And this chart right here perfectly illustrates the single biggest trade-off in all of manufacturing: precision versus cost. A loose tolerance, say an H11, is cheap to make. A general-purpose one, like H8, costs a bit more, but the second you demand high-precision tolerances like H6, the cost doesn't just climb, it explodes. Why? Because now you need more expensive machines, intense quality control, constant tool changes, the whole shebang. This is the central conflict, and the key to great engineering isn't making everything perfect. It's choosing the loosest possible tolerance that still gets the job done right. Okay, let's head down to the workshop floor and see how this all actually comes together. We've talked about the design code, but how are these perfect fits actually made in the real world? So this is how those funny little codes translate into actual jobs. If you need a shaft to rotate with very little friction, you're going to spec out a clearance fit, like H7/G6. If you need a dowel pin for super precise location, that's a job for a transition fit, H7/H6. And for something like a gear hub that has to transmit torque without ever slipping, you'll call out an interference fit, like H7/P6, which means it has to be pressed fit during assembly. Today, our CNC machines can hold tolerances that were just science fiction a century ago. But what happens when you need a level of precision that even the absolute best machines can't deliver? Well, that's when we enter the amazing world of hand fitting, a craft where the ultimate accuracy is achieved not by a computer, but by human skill. We're now going beyond what standard machines can do into the realm of the truly perfectly flat and impossibly smooth. These are techniques that kind of blur the line between engineering and straight-up artistry, and they're used to create the master surfaces that all other precision is measured against.
One of these incredible techniques is called lapping. Just imagine taking two metal plates and rubbing them together with a gritty paste in between. The tiny abrasive particles roll and slide, and they slowly wear away the microscopic peaks on both surfaces. Over time, this process just averages out every single imperfection, and what you're left with are surfaces that are almost perfectly flat and unbelievably smooth.
And the results are just staggering. I mean, look at this. The top image shows a surface straight off a lathe. At the microscopic level, it looks like a jagged mountain range. But then look at the bottom image. After lapping, those mountains have been worn down into this stunningly flat plane. It's night and day. So just how flat are we talking here? Lapping can achieve a flatness of 1/10 of a micron. Let me put that in perspective for you. That is 1/10,000th of a millimeter. A single human hair is about 70 microns thick. This is a level of precision that is just mind-boggling, and it's often achieved by combining machine work with incredible handiwork. Okay, so we've gone from this huge picture of global supply chains all the way down to the microscopic world of surface finishing. Let's pull back out and talk about why this whole invisible system is so incredibly important.
It really all comes down to making smart choices. On one side, you have something called over-tolerancing. It's a really common mistake where engineers specify fits that are way tighter than they need to be. This just leads to wasted money, delayed projects, and a huge pile of rejected parts. But on the other side, you have smart tolerancing. This is the real art form, understanding exactly what a part needs to do and then choosing the most efficient, most cost-effective tolerance to get it done.
So what are the big things to take away here? Well, first, ISO standards are the invisible language that lets our global economy actually work. Second, the job of the part always determines the fit. Does it need to move, just sit there, or stay put forever? Third, and this is a big one, remember that chasing unnecessary precision gets crazy expensive, fast. And finally, even in our super high-tech world, the absolute pinnacle of accuracy can still depend on the skill of a human hand. This whole system, hiding right there in plain sight, is truly the foundation of our modern world. And that kind of leaves us with one last thought to chew on. As our machines get more and more precise, more and more automated, you have to ask, what's the future role of human craftsmanship? Is there a limit to what machines can do? A final frontier of perfection that will always require the subtle touch and the keen judgment of a skilled human hand.